Okay, so guys, in this video we're going to be looking at angular momentum. So let's just put in a little heading here, angular momentum. And with angular momentum, what our goal is to look at the idea of conservation of angular momentum in this video. And so some of the objectives are going to be to recognize conditions under which angular momentum is conserved and relate this to other systems like satellites that are orbiting. Also state the relationship between net torque and angular momentum, because if you think about it, torque is the rotational analog of force, and we know that from the impulse idea that if you apply a force to an object, you change its momentum. And so that idea is very important. Now, the instantaneous change in momentum is force, right? So dp dt, so instantaneous change in momentum with respect to time will give you force. And so we're going to see how does that affect angular momentum. If we applied a force and changed the linear momentum, perhaps now if we applied torque, we'll change the angular momentum. So that's one of our objectives. So analyze some problems in which the moment of inertia of an object is changing as it rotates freely about an axis, a fixed axis. And then we'll maybe even look at a collision between a moving particle and an object that is rotating. So if we remember our definition of angular momentum, it's going to give is R cross P. So R cross P is our major definition. We also had I omega as the other option. And now what we want to see is what if we take an instantaneous change in angular momentum like we were talking about with angular velocity. So if we say, what if I do dl dt? What if I take that angular momentum? Now obviously I'm going to do take the derivative of the right hand side as well, and we actually haven't talked about how to take the derivative of a cross product, so I'm going to show you the rule, and unfortunately that's going to be one of the things I'm not going to prove, but you can either go online and do some research on your own, or perhaps wait for a time when your math class will fill in the gaps. So let's just quickly look at the rule for that, and then we'll keep going. So the rule for taking the derivative of a cross product is going to be, if I take the derivative with respect to time of this cross product, A cross B, the result is going to be, I'm going to have the derivative of A, of vector A with respect to time, cross the B vector, and then I'm going to add the A vector cross the derivative of the B vector. And so that's the rule that we're going to use here. So let's try to apply it to the system where we're doing dl dt. And when we're doing dl dt, we're actually doing d times r cross p, which is the rule. And then we're doing that with respect to time. So let's try to write it out in that form. Let me just move this up here. Give us a little bit more room. And let's try to actually write out what we saw. So we're going to do dr dt cross p plus r cross dp dt. And let's see what we come to get there from this formula. So let's try to simplify this. And if we do dr dt, that's position, derivative of position with respect to time, that's going to give us velocity, right? That's going to be velocity cross p plus r cross dp dt. And in the beginning of the video when we were discussing the objectives, we recalled that that's actually force. Okay, so this is interesting here, and you probably are starting to notice a few things here. R cross F plus V cross P. Let's see what those end up being. I'll try to rewrite that slide. We've got V cross P plus R cross F. Now let's do a little bit more simplification so we can analyze sort of what's going on here. So if I do V cross P, that's basically saying V times P times the sine of the angle between V and P plus R times F times the angle times the sine of the angle between r and f. Well, v and p point in the same direction. They have to, right? We already established that idea before, that velocity and momentum always point in the same direction because velocity makes up momentum, and they are naturally then going to point in the same direction. And so Vp times the sine of 0 is actually going to be just 0 plus r cross f, or f cross r. Well, you may remember that as torque. Okay, so that's actually torque. And so what we can write is that the derivative of angular momentum with respect to time is actually torque. And that's a really useful tool. Now, if we put that next to one of our old understandings, and we said the derivative of momentum, linear momentum with respect to time, well, that came out to be force. So you can kind of see that these rotational analogs of each other actually make sense and are consistent with the rules that we've been following. So that's a useful tool, and that makes a lot of sense if you think about what does this actually mean, right? What does this actually mean? Well, a torque on an object is going to change the angular momentum. And so a force that is applied at some distance r from some axis of rotation is going to cause a torque that will cause the object to begin to spin, which will result in a change in angular momentum. So that's a very obvious thing. Now let's actually get down to the idea of conservation of momentum, because that's what we've really set out to do on this video. Let's go to a new slide and take a look at that idea of conservation of angular momentum. So the conservation of L, or angular momentum, spin angular momentum, the product of an object's moment of inertia and its angular velocity. So let's write that out. I omega, moment of inertia and angular velocity, about the center of mass, is conserved in a closed system with no external net torque applied, which is the same thing as conservation of angular momentum. And if we write this out in mathematic terms, that means that L naught is equal to L final, which is I naught omega naught is equal to I final omega final. And so let's do some applications of that. Well, the ice skater example. An ice skater spins with a specific angular velocity, and she brings her arms and legs closer to her body, reducing the moment of inertia of her body to half its original value. What happens to her angular velocity? Well, if we look at this equation, I'm going to divide. We want to see how her angular velocity resolves at the end, what will happen to her speed. And if you've seen this happen, you kind of know the answer, but let's look at why. So her angular momentum initially is, say, let's make it 4. And her angular momentum at the end is 2, right? So her new velocity is actually going to have to end up becoming doubled, right? Because if I naught omega naught equals I times omega, then if I half this value, this is going to actually have to double in order to stay the same momentum, and that's why they'll get faster. Ballet dancers do the same thing, and they use their legs and their arms as well, except they're not on ice, they're on their toes, and so there's a little bit more friction involved. They won't spin as fast, but pretty darn fast as well. Let's look at what would happen to a rotational kinetic energy. That's an interesting one. So rotational kinetic energy is going to be equal to 1/2 I omega squared, which is the rotational analog of all the things we've been talking about. And let's see what would happen if her moment of inertia reduced to half. If we said this would have to double as a result, and if that doubles, that goes up in this equation would go up by 4, but you've already halved the moment of inertia, so the end result is that K would double. So she would have double the kinetic energy, which is quite interesting. So that's kind of how the moment of inertia is very specifically added. Let's just do one more problem just to kind of make sure we've got this down. In this problem, a disk with a moment of inertia of 1 kilogram meter squared spins about an axle through its center of mass with an angular velocity of 10 radians per second. So let me just draw that really quickly. So we've got this disk that's spinning around this axis. Okay, sorry, this drawing's not very good. And it's got a moment of inertia of 1 kilogram meter squared. And the initial speed, angular velocity, is 10 radians per second. Alright, an identical disk which is not rotating is slid along the axle until it makes contact with the first disk. If the two disks stick together, what is the combined angular velocity? So we'll have a second disk over here, and it's going to move towards that. So we know that angular momentum is conserved, so, sorry, that's the wrong letter. Let's write L equals L. So I omega equals I omega. And we want to know what that final velocity is. So I end up with I omega divided by I should equal the omega final. So the initial I is going to be 1. Initial speed is going to be 10. I'm not doing any units here. The final angular momentum, well, what would that be? We know that the thickness is not going to matter per se. We've established that through all our derivations of those formulas. There's all the mass is still located at a uniform distance from the axis of rotation, but now what's going to be different is just going to be double the amount of mass. So if we have double the mass, we should have double the moment of inertia, and so that should be divided by 2. And so that would be 10 divided by 2, which is 5, and the units here are radians per second. We're looking at the speed. And let's try to analyze that and see if that makes sense. A disk that's spinning at 10 radians per second collides with an identical disk, and they stick together, and now they're going to be spinning with double the amount of moment of inertia, so their angular speed should halve, and that is what happened. So hopefully that helps. We'll have some practice problems as well that you can do some independent practice on this concept.